Hello and welcome to this short clip having a look at a review of Kw and the ionic product of water, followed by an applied exam style question afterwards. So let's look first of all at the dissociation of water, which is what the Kw expression refers to. So it's obviously in equilibrium, and if you draw the displayed formulae of everything, you can see that there's a bond being broken in water, so it must be an endothermic process because breaking bonds require energy. In terms of equilibria, that must mean if the temperature rises, the position of equilibrium shifts to the right in the endothermic direction. So if we take the standard value of the ionic product of water given in data sheets that are provided in A-level exams, it's usually the value that we find at 298 K. So what happens if you increase the temperature? So that'll make more dissociation happen. Therefore, Kw will increase in value as the temperature rises. So let's explore that for a moment. So here's some data. Let's try and justify why the numbers get bigger as the water gets hotter. So if we go back to our original dissociation and think about what's happening as we go down that table. If we were to write an equilibrium dissociation expression, or Kw expression in this case, for the dissociation of water, you'd have concentration terms for H plus, OH minus, and also water. However, the concentration of water will remain largely constant before and after dissociation, so it's assigned a value of 1. So that gives us this particular version of it over here. So what's going on? So as the temperature rises, as we said, more OH bonds in water are broken. That shifts the position of equilibrium to the right. So if we make more hydrogen ions, because the position of equilibrium is going in this direction, that numerator will increase, so therefore Kw will also go up. So now let's look at a question that tests your knowledge or application of this out a little bit. It says the pH of pure water at 323 Kelvin is 6.63. And if we put the ionic product of water up again, it says using this value, calculate the value of Kw at this temperature. So the pH is obviously going to be related to H plus through 10 to the minus pH. So if we plug that into our calculator, that gives us 2.344 times 10 to the minus 7. You'll notice I've put 2 dots after the 4 there because it's a very long calculator value. So I'm keeping my calculator value as I go throughout. So going back to Kw, it's H plus and OH minus, the two concentration terms. But because they're made in equimolar quantities, you can assume that H plus squared could be the same as H plus times OH minus. So that gives us 5.495 ... times 10 to the minus 14 moles squared decimated to the minus 6. The next question asks us to consider the pH of pure water at 298 K. It's saying the pH is 7 at this particular temperature. They want us to check or think about whether water is more acidic at 323 Kelvin and to explain why. So I'm going to say water is not more acidic because acidity and pH is linked to H plus ion concentration. But when OH minus is produced at the same time and in equal quantities, all of those H plus ions will be neutralized. So therefore it's not more acidic even though the pH will go down. So they want the pH of a solution of 0.1 mole per decimeter cubed sodium hydroxide at 323 Kelvin in part C. Again, we write out Kw and we put in what we know. So we know the concentration of OH minus because the question told us. We know the Kw value at 323 Kelvin because we've just worked it out in part A. So all you have to do is rearrange so that H plus concentration is the subject. So that gives us 5.495 times 10 to the minus 13 moles per decimeter cubed. You just plug that into pH equals minus log H plus, and that gives us 12.26 to 2 decimal places. Now the actual calculator value will be longer than that. You always round to 2 decimal places for pH. Okay, hopefully this has been a useful quick look at Kw once more. Until next time, thanks for listening and see you soon.